Welcome back to The Explainer. Today, we're stepping out of the ordinary and into a totally futuristic electronics lab to witness the birth of what I like to call a silicon superhero. Picture this. Lying on a workbench, bathed in the blue light of holographic displays, is this seemingly simple electronic component. But hit it with a massive surge of energy, and suddenly it comes alive. It's like it transforms into this towering figure in red, black, and silver armor. We're talking about the TIP42C, a heavy-duty PNP power transistor. And honestly, once you hear its story, you are never going to look at the circuits powering our world the same way again.
So here is the big question. How exactly does a tiny, completely unassuming three-legged component control just massive amounts of electrical power? It's kind of the ultimate mystery, right? It fascinates beginners, and it still blows the minds of seasoned engineers. You might look at it and just see another boring piece of hardware. But hidden inside those three little legs is a brilliant mechanism, acting as the ultimate gatekeeper for literal surges of energy. No magic here, just incredibly precise, reliable semiconductor physics. Let's dig in and see how it actually works.
All right, let's hit the specs, starting with this massive number, 100 volts. This is the TIP42C's collector-emitter voltage capacity. In the high-stakes, high-pressure environment of electronic design, this little transistor can withstand a whopping 100 volts across its main terminals without instantly breaking down. I mean, that is a serious level of electrical pressure, making it an absolutely rugged, dependable choice for high-voltage environments.
But wait, the sheer strength doesn't stop there. 6 amps. That's its collector current limit, meaning our silicon superhero can comfortably handle a continuous flow of 6 amperes of electrical current just rushing right through it. To put that into perspective for you, 6 amps is more than enough to drive some really heavy-duty motors, light up massive arrays of LEDs, and push booming heavy bass through giant loudspeakers. It is literally a workhorse. Now, when you bring all these specs together, they essentially form our character's armor. It's a PNP bipolar junction transistor, and it's housed in this super durable TO220 package. But I want you to pay really close attention to this specific detail, a maximum power dissipation of 65 watts and an operating temperature that can skyrocket up to 150 degrees Celsius. That 65-watt figure is no joke. As we'll get into a bit later, wielding that much raw power requires some serious cooling, or our hero is definitely going to overheat.
Section 1. Inside the silicon armor, the anatomy of a transistor. Let's shrink down and see what actually gives this thing its power.
If we could look right through the outer shell, we'd find 3 alternating semiconductor layers, the p-type and n-type layers. Millions of positively charged holes hang out in the p-type material, while electrons are bouncing around inside the n-type region. This alternating structure is exactly what makes it a bipolar junction transistor, or BJT. And here's a super crucial takeaway, especially if you're new to this. Unlike a MOSFET, which is entirely controlled by voltage, a BJT like our TIP42C uses a very small current to control a much larger current.
Think of the transistor like a futuristic walled city. You've got the emitter, that's your massive power station just bursting with positive electricity. Then you've got the collector, the busy industrial city, full of machines just desperately waiting for all that power. But standing right between them, that's the base. The base is basically an intelligent security control center. It operates these giant gates blocking the path from the power station to the city. And under normal, resting conditions, those gates are locked down tight. Nothing gets through.
But we definitely don't want those gates closed forever, do we? This brings us to Section 2, the power of amplification. Opening the gates. Prepare yourself because we are about to witness the transistor's ultimate superpower.
So, here is how the action actually unfolds. Step 1. An external circuit gently pulls the base voltage lower than the emitter by just about 0.7 volts. That's it. But the moment that happens, Step 2, boom, those giant microscopic security gates swing wide open. Which leads to Step 3, brilliant, massive streams of electrical particles rush smoothly out of the emitter straight through to the collector. By doing nothing more than pulling the base negative relative to the emitter, our transistor springs to life.
And the real magic here? It's all in the ratio, 30 to 75. This is the transistor's current gain, also known in the biz as beta or HFE. Let's say the transistor has a gain of 50. That means just one tiny unit of current flowing out of the base allows 50 units of current to come crashing through from the emitter to the collector. Picture a massive water pipe. The base is just a tiny little control valve tapped into the side of it. Turning that tiny valve regulates an absolute roaring river of electricity flowing through the main pipe. Small control current, massive load current. It's brilliant.
Section 3.
3 operating regions, mastering the flow. Because, being a hero isn't just about raw power, it's about control.
There are 3 specific states you need to know. First, the cutoff region. If the base isn't pulled low enough, the gate stays shut. 0 current flows. It's basically acting just like an open switch. Next is the active region. This is where the magic water valve stuff happens. It acts as a current amplifier, smoothly adjusting the collector current so it's perfectly proportional to the base current. And finally, we have the saturation region. If you pull that base hard enough, the transistor is fully on. It behaves like a completely closed switch, just dumping the maximum possible current straight to the collector.
Now, our guy isn't the only transistor in the lab. Welcome to Section 4, the duel of transistors, PNP versus NPN.
Imagine 2 rival characters standing side by side. We've got our hero, the TIP42C, which is a PNP transistor. Like we literally just saw, it turns on when its base becomes negative relative to the emitter. But check out its partner, the TIP41C. It is an NPN transistor, and it plays by completely opposite rules. It turns on when the base becomes positive relative to the emitter. If you were looking at the charge carriers and the current flow, you'd see everything moving in entirely opposite directions. They are perfect mirror images of one another.
All right, theory is great, but the battlefield of a real circuit board, that's a whole different story. Section 5, Real-World Action and Thermal Management.
When you step into the real world, the TIP42C is absolutely everywhere. It's out there pushing power to massive, high-current LED lighting systems. It's switching heavy DC motors on and off without breaking a sweat. It's operating critical relay circuits. It's stabilizing touchy voltage regulators. And it's the muscle driving the booming loudspeakers inside your favorite audio amps. For medium and high-power designs, engineers rely heavily on this thing to just get the job done.
But, and this is a massive but, with great power comes incredible heat. Remember that 65-watt power dissipation limit from earlier? Yeah, if you push maximum current through this thing, a thermal camera would show it literally glowing white-hot. That is why there is a strict, non-negotiable rule for high-current operation. You absolutely must attach an aluminum heatsink to its metal TO220 tab. This chunk of metal instantly draws the heat away, dropping the temperature and keeping the component safely below its limits. Without it, you're looking at catastrophic thermal failure.
As we wrap up our time in the lab, I want you to imagine our hero delivering one final, dramatic thought. Never judge me by my 3 small legs. Inside me lies the power to control massive electrical currents with absolute precision and reliability. Whether I'm amplifying music, switching motors, or regulating power, I quietly help bring modern electronics to life.
And that officially wraps up today's explainer. We've covered how it works, how it amplifies, how it switches, and how to keep it from melting down. But now I want to leave you with this. Look around the room you're in right now. Look at your appliances, your speakers, your gadgets. Where might these unseen silicon heroes be hiding, quietly managing the massive electrical currents in your very own home? Keep wondering, keep exploring, and I will catch you in the next explainer.